Okay, so what we did last time is showing that the condition that the discriminant is non-zero for an algebraic curve of the type we are interested is equivalent for the curve being smooth, that is to admit a tangent line at every point. And I would like to start today with filling a gap. In fact, if you remember the proof that we did last time, we said that for algebraic curve of the form y squared equals x cubed plus ax plus b, delta of E, which is this 4a cube plus 27b square, is non-zero if and only if E has a tangent line. At every point. And the proof, this is usually the case. I mean, polynomials are admit tangent line for almost all the points, and there are only a small number of points in which an algebraic curve could possibly be non-smooth or to not admit a tangent line. And what we said, the interesting case of the proof this last case maybe is that the tangent line that we are looking for needs to, so if p is x0 y0, then the slope of the tangent line is 3x0 square plus a over 2y0. This is m. And of course, it could be that I mean the numerator and the denominator are zero. This is the non-trivial case. All the other cases, it's easy to show that there is a tangent line, possibly vertical, but if 2y0 is 0 and 3x0 squared plus a is also 0, then what do we do? I mean, what we did is we substitute, I mean, instead of a, we replace minus a, because clearly for negative a, the second condition cannot happen. So, sorry, for positive a. So in this case, necessarily a is negative, so I replace it by a positive, which means the condition is now 3x squared, sorry, x0 squared minus a is equal to 0, which is equivalent to say that x0 squared, sorry, 3x0 squared is equal to A. Now, what I did last time is I said, okay, this means that x0 is the square root, or maybe plus minus the square root of A over 3. And then I substitute it in the equation, and I find out that this implies the, in fact, equivalent, that delta of E is 0. So and this completes the proof. It shows that this last case cannot happen in an elliptic curve. But can somebody tell me what is the problem with this argument? I mean, remember, we're talking about over a general field, arbitrary. Okay.
The square root might not be defined?
Exactly. Yeah. So square root is not a feature that you can have in every field. And you, I mean, I didn't cook up an example, but you can easily take small primes and find elements in some prime field for which there is no square of this element. I mean, square root. But this is not kosher. So to speak. I mean, it's not meant to be a religious proposition, but just to tell you that you cannot do the usual operations that you are used to in real numbers over a general field. So not everything is passes through. So I need a way to circumvent this process. So instead, I get x0 equals A over 3. Sorry, x0 square equals A over 3. By the way, A over 3, it might also not be defined if we are in a characteristic 3, right? Because in characteristic 3, 3 is 0, and then I don't have, I cannot divide by 0. But our assumption is that the characteristic of the fields is always different than 2 or 3. So I can divide by 3. And now I do the following. I know we have x0 cube plus, sorry, minus ax0 plus b equals y0, but y0 is 0 in our case, so it equals 0. And now I plug in this x0 square. I get x0 times a over 3 minus a x0 plus b equals 0, which is equivalent to say that x0 is minus 2 over 3 times b over a. Okay, and now I take this and I plug it in the triangle equation, and I get that a over 3 is equal to 9b squared divided by 4a cubed, sorry, a squared, which is equivalent to say that 4a cubed minus 27b squared is equal to 0. And now I substitute back minus a instead of a, and I get that this is 4a squared, sorry, 4a cubed plus a 27b squared equals 0. So we get that the condition of having a well-defined, a tangent line at the point P, for which both the numerator and the denominator are 0, is equivalent to say that the discriminant is non-zero. So this gives us smoothness. Any questions about this correction? Any other questions about what we did last time? Okay, so I remind you that the k rational points, so let's say E over k is an elliptic curve. The k rational points, which I denote as E with brackets k, is the solution set for the polynomial. So it's all the x comma y in k squared, such that y squared equals x cubed plus ax plus b. Union, I have to add one other point, which I call the point at infinity. And this will serve as the neutral element for the group law that we are going to define. And what I said last time is a kind of how to view the group law geometrically over the real numbers. But okay, let me maybe repeat. I mean, you take this elliptic curve, take 2 points, say P and Q. You pass the line between P and Q. This line has to intersect the curve in a third point. This is P, maybe we can denote it as P star Q. And then I reflect along the x-axis to get what I define as P plus Q. Okay, so my drawing skills again are not very good, but intuitively, because the curve is a cubic, is of degree 3, then generically a line I mean, a line intersects a cubic in 3 points. Of course, there could be lines that do not intersect the cubic in 3 points. For example, you take the tangent line here, this tangent line intersects the point, or I mean the curve, only at one point. But we have this point at infinity, which we think, again, for now, just intuitively, as lying at the top and at the bottom at the same time. So I can say that these are the k rational points, right? I can say that if I add this point at infinity, then even this tangent line intersects the curve at 2 points, right? At the point at infinity and at p. In fact, and we will not get into this rigorously, one can define the multiplicity of a intersection. And it turns out that this point P will have intersection multiplicity 2. And so using a correct notion of multiplicity, one can say that a line intersects a cubic always at 3 points if you count multiplicity correctly and you have the point at infinity. Okay, so this is the general intuition. And now we need to make it at least well defined over a general field. So okay, so now we have let's say of this operation plus over a general field. So I start with 2 points. P is x0, y0. Or maybe, sorry, I do 1 here in the notes. And Q is x2, y2. And let L be the line between P and Q. So L is of the form y minus well, I guess we could say y equals mx plus y1, where m is, I mean, if it is defined, y2 minus y1 over x2 minus x1. So yeah.
So the bar over P and Q, where like L is equal to P bar. This is
L is the line between.
Oh,
I mean that passes. I was trying to make a shortcut. The line that passes through P and Q. Okay. So we have this line. If x1 equals x2, then in fact the line must be vertical. I mean, the x1 equals x2, it means that I have this, let's say, P is here and Q is here. And then the line that passes through them does not, well, it has an infinite slope. So, so M is not defined, but still the line is defined. So vertical, and we deal with this later. So suppose x1 is different than x2. Now we have the equation of L, right? Y equals M x minus x1 plus y1. I think I had a mistake here. This should be x minus x1. And I want to find the intersection of L with E. And so I substitute, instead of, I substitute this, this thing into the equation of E. I get that M x minus x1 plus y1 square equals x cubed plus ax plus b. So this is a this can be rearranged as a cubic, right? This is equivalent, after some calculation, to the equation 0 equals x cubed. And now what's the coefficient of x squared? The coefficient of x squared is simply m squared. Sorry, it's a minus m squared. And there are other things, but I don't care about the other terms. Now, this is a cubic equation. We know that x1 and x2 are roots of this equation, star. And also, I mean, over the algebraic closure, I can write x minus x1, x minus x2, x minus x3 equals 0. Okay, it's the same. It's just another representation of this this equation that at least a priori we only know it is valid over the algebraic closure. But if you open this, this I think we had less time, or maybe a session before that. This is equivalent to say, and this is always true in a cubic, that you get x cubed minus x1 plus x2 plus x3 x squared plus some other terms equals 0. Okay, this is what happens when you open up this this equation. And we know that this is an equation. It's the same as we have here in the purple one, which is a polynomial over k, not over k bar. So we conclude that x1 plus x2 plus x3 is equal to m squared, which is an element in k. And since already x1 and x2 are in k, it follows that x3 is also in k. Okay, and not in k bar, that is kind of inaccessible. Okay, so now we're almost done for this case, because we have the x coordinate of the intersection, right? We have this line intersect the curve at p star q, and we have the x coordinate. The x coordinate of this is x3. What is the y coordinate? The y coordinate is easy, because I know that I know that this p star q must lie on the line L. So y3 is equal, y3 is equal to minus the y3 that we have in p star q, that is m x minus x3, x minus x1 plus y1. So p plus q is defined as x3, y3. Okay, and this is valid in any field. Any questions about this this case? Yes, Nicolas.
I'm still unclear exactly, because the first star that you see here, you said it was defined over the algebraic closure, and then you say, okay, x3 must be on k, not the algebraic closure. And I'm sure how you made this gag. Yeah, how did you pass from the algebraic closure to the reduced one?
Okay, so I'm saying we have this this cubic here in purple, right? And like any cubic, like any polynomial, I can factor it linearly over the algebraic closure.
Yes.
So I know that over the algebraic closure, I have this guy.
Yep.
And this guy has to be equal to, these two things have to be equal.
Mm-hmm.
So now I open up the brackets in maybe we call it double star. Okay. I open up the brackets in double star. I get, here we can say triple star, right? I didn't do the calculation. It's a bit
Sure. Yeah, but I understand.
Okay, but this you can believe. I get triple star. So now I know that triple star has to be equal to star, right? As a polynomial equation.
Yep.
So it means that minus m squared has to be equal to minus x1 plus x2 plus x3.
And since m is in k, so all the 3x are in k as well.
Yeah. Since m is in K, then m squared is in K, and since x1 and x2 are in K as well, then x3 is simply, you know, m squared minus x1 minus x2.
Makes sense. Thank you.
Okay. What about the other cases? So this is a definition of the binary operation for any 2 points that are not equal and that don't have the same x coordinate. Okay. In case, yes.
Can you list all the cases we want to consider?
I will. I didn't write it very organized in the notes, so I will list it as we go along,
Okay.
if that's
Thank
okay. I mean, basically, we want here. I should say this is the generic case is that P is not equal to Q, x1 is not equal to x2, and also P and Q are not the point at infinity. But, you know, if P and Q, if one of them is the point at infinity, or even two of them, then we know what we have to do, because the point at infinity has to be the, I mean, we want it to be the zero element of the Grup law. So this is easy. In case x1 is equal to x2, but y1 is not equal to y2, right? Then the line is vertical. We said it. Then L is vertical. And then, of course, L cannot intersect the curve in any finite point, but it will intersect the curve in the point at infinity. Right? This is we will have this. The case is the purple case. This line will intersect the k rational points at the point at infinity. So, of course, in this case, we define P plus Q is equal to, well, it will intersect the k rational points at O, and then we have to reflect. But reflecting O is just O again. So I guess if you want it by steps, you could say that the star is O, and hence P plus Q is defined also as O. Is that the reflection of O is O. And now, what is the case we are left with? The case we are left with is if P is equal to Q. And of course, P and Q are not the point at infinity. I mean, again, the point at infinity, it's we know how to add 0 to 0 in anything that needs to be a group. This is trivial. But what happens in the P equals Q case? I mean, Or maybe let me just remark on the last case, this is the last case we discussed, P and Q, and we said that P plus Q is 0 or O. This means that if we are about to have a group, then P is equal to minus Q. Okay, so the additive inverse in the the additive inverse, if we have a group, then the additive inverse would have to be simply reflecting along the x-axis. Again, reflecting along the x-axis is just to help you psychologically, but over a general field, I simply put a minus in front of the y coordinate. Okay. So this is the case we had before, and now maybe I need to choose another point for the drawing. Now I want to add a point to itself. This is called in cryptography, people call it doubling a point. So to double a point, I need to draw the line that passes through P and Q. This is like the tangent line to E at P. And I claim that this tangent line will intersect E exactly at an additional point. This would be P star P. And then I will reflect and we'll get P plus P. Okay? But I need to show it algebraically. Yes.
Do we say that double, do we split double from addition to itself of an element such that everything holds up together? So what I'm trying to say is, if we sum an element to itself, since one is in the top of the other, you can kind of draw the tangent line to intersect in different, like the line that touches both can go anywhere, to put it in some sense. So that's why you define double? Or no?
No, I call it doubling a point is simply adding it's just a term that people use in cryptography. In elliptic curve cryptography is like just adding a point to itself according to the elliptic curve Grup law.
But, okay, maybe this is advancing to the thing, but doubling and adding have different.
No, okay. This we will later denote it as 2p.
Okay, fair enough.
Okay, and this is in accordance to a notation we already had in abelian groups, right?
Okay, yeah, makes sense.
Okay, so this is why it's called doubling. Okay, so this is the kind of the geometric intuition, but let's do it algebraically. This is L, right? The slope of L and P is say x1 y1. And so the slope is 3x1 square plus a over 2y1. Okay, now if y1 is equal to 0, which is, it means that the slope is not really defined, then L is vertical. If L is vertical, then of course then P, let's say P star P, would be the only possible intersection of the vertical line with the k rational points, which is 0. And this means that P plus P is 0. So this tells you that the points here, and possibly if we had like a small lake here, then also these points are points that, according to the group law, if you add them to themselves, you get 0. So this is called the two torsion points. Okay. Otherwise, so I know that y1 is not 0. If y1 is not 0, then the equation of L is given by y minus y1, or maybe y equals m x minus x1 plus y1. And again, I substitute it. Now, I define g of x to be this x cubed plus ax plus b minus m x minus x1 plus y1 square. And clearly, g of x1 is 0, right? Because we know that p lies on the curve, and p is x0, y0. Sorry, x1, y1. Now, how do we find the other root? Here we have a bit of a problem, because the argument we had before was assuming that we have two distinct roots. If we had two distinct roots, then we know that the third root over the algebraic closure must be in fact in the field K, and then we find that this will be the x coordinate of the result we are looking for. But here, what is happening is, in fact, because it's a tangent line, the x1 is a double root. We claim that x1 is a double root of G. And this is very easy. I take G prime. First, I do it generically. So for general x, it's going to be 3x squared plus a minus 2m to m mx plus y1 minus mx1 . And now I substitute x1, and I hope you can believe me that you get 0. It's an easy calculation with substituting m for being this expression. Okay, so x1 is a double root. It means that this cubic gx, which I know over k bar, it is equal to x minus x1 square times x minus x3, let's say. Which means that the coefficient of x square, which is minus m square, must be equal to m square must be equal to the sum of all the roots, that is x1 plus x1 plus x3. This is just as before, only that instead of having two distinct roots x1 and x2, I have a double root x1. And this means that x3 is m squared minus 2x1, which is an element in K. Thus, that's the only possible. This shows you, by the way, that there could be no other intersection point of the line with the curve. Okay. Also, in the previous cases, there could be no more than 3 intersection points, because intersection points would have x coordinates being a root of a cubic, and there could only be 3 possible roots of a cubic. And this, in this case, p plus q will be this x3 and minus, we have the line L. So y3 is going to be m x3 minus x1 plus y1, and we need to reflect it, so it's going to be minus m x3 minus x1 minus y1. Okay. Yes.
I'm a bit confused how we introduced G prime.
G prime is the derivative. It's the formal derivative.
Ah, it's not G prime, it's derivative. Okay.
Yeah, maybe.
Then it is clear. Then it is clear.
It's a maybe it's a good standard to write the derivative like this in our because we don't do a lot of derivatives. The only thing we do is like formal derivatives of polynomials, and then I want to reserve the prime to just denoting another function. So maybe I will denote it as D. Okay, this derivative. We had a lemma. This I mean, this appears in the note. I don't remember exactly where, but we definitely talked about it. That an element in a field is a double root of a polynomial if and only if it nullifies the polynomial and the derivative of the polynomial, right? Okay, so just to show you that kind of the things are also defined with the point at infinity. I mean, how do I add the point at infinity? According to the kind of geometric intuition we have, is I draw the line. let's say, how do I add the point at infinity to itself? I draw the line between itself, I mean, between the 2 points, and I look for the intersection. The intersection is again the point at infinity. You reflect, you get again the point at infinity. So this is kind of, but this is really not necessary. I mean, since this is going to be the neutral element, we know that O plus O has to be O. Okay, so this defines, yes.
Maybe this is stupid, but can we understand the point at infinity as a subfield of a single element? Well, no, not as a subfield because it doesn't have an inverse. But I mean, it's like another.
I will talk about it in the next part of this lecture.
Okay.
This concerns the projective space. We talked a bit about the projective space, and one can define the projectivization or the elliptic curve in projective coordinates, and then you have a precise meaning of what is the point at infinity.
Okay, thank you.
Okay? But just to say, I mean, what I defined here is also well defined. It's not hand waving, as mathematicians say. I mean, we introduced a new symbol O, and I defined a binary operation, and this binary operation is well defined for every pair of points in the k rational points ek. Okay. Yes.
This is maybe a little slightly off topic, but I think there are also other type of curves where you don't need to have special cases that we call complete addition formulas and things like this. And will we be seeing those, or?
This is the projective. I think in the projective coordinates you have a cleaner formulation.
Well, it depends on the type of the curve. Like short wire structure don't have this, but I think twisted Edwards and things like this have. Where you don't care about if it's a 0 or not 0, this. That makes it easier to be to have constant time as well implementation.
Yeah, there are we can. I mean, there are different types of coordinate systems to define elliptic curves. I forgot. There are various names, and in different coordinate systems, you might have a cleaner definition. Mm-hmm. That's true, but this is mostly important for implementation. And for us, we are going to stick with this this definition because we need it for kind of theoretical development. I could later on do a session on I forgot the names, but different coordinate systems for elliptic curves. But it's rather technical, and I think I mean it would not help us directly in any of the things we do. So
thanks.
Yes, there was another question. Maybe in the chat.
No, sorry, I just linked. There's a paper that indeed derives complete formulas for sure by plus terms. So, yeah, you don't need to use twisted Edwards or whatever.
Yeah. So in general, what I will try to do henceforth is to avoid most of the computations, because it's not helpful, I think, for also for the audience. I mean, this is something you need to either do yourself or like let a computer verify. But still, it's important to know. It's important to understand how this is defined over a general field. All right. So
sorry, Matan. One more question, just to understand. You said we will not be going through all of the different coordinate systems. But this also implies we will not go through different types of curves, like Montgomery.
What-
It was
What we do here is completely general. I mean, any elliptic curve over a field with characteristic that is not 2 or 3 can be expressed in this form.
okay. Okay, that's why we build short bias transpace or bias
Yes.
That's why we built it. Okay, fair enough.
So we are not losing any generality apart from this characteristic 2 and 3. But of course, in terms of implementation, there could be, I mean, there are better ways to, I mean, efficiently compute the stuff we talk about.
Okay, thank you very much.
Okay, so I suggest we take a 10 minutes break and we come back to the projective version of elliptic curves.
See you now.
Okay, can we start again? All right. So the next thing I want to talk about is called the projective coordinates. We talked a bit about the projective space, just in terms of terminology. What we did in the previous hour is called affine. So this is the distinction is affine geometry or affine coordinates and projective coordinates. We saw a definition, but let me repeat it. Let K be a field. And consider the affine three-dimensional space over K, which is, I remind you, it's simply K times K times K. And now I take the affine space and I remove the origin. And I want to define an equivalence relation, which I call tilde, on the collection of all points in the affine space, the affine three-dimensional space, without the origin. And I do so by setting x, y, z equivalent to lambda x, y, z for any non-zero element lambda. Maybe exercise. Tilde is indeed equivalence relation. I can give you a sketch. I mean, the non-trivial thing in equivalence relations is to show transitivity. So if you have x1, y1, z1 equivalent to x2, y2, z2, and you have in addition that x2, y2, z2 is equivalent to x3, y3, z3, then let's say x1, y1, z1 is equal to lambda, say lambda 1, x2, y2, z2, and x2, y2, z2 is equal to lambda 2, x3, y3, z3. And then you just multiply the lambdas, you get that x1 y1 z1 is equal to lambda1 lambda2 x3 y3 z3. Okay, reflexivity and symmetry is very easy. So we have like this equivalence relation. The way to view it, or okay, maybe just the projective plane is this set, the affine space, minus the origin. This is a set with an equivalence relation, and I can take the quotient. This is called PK2. Okay, notice the change in dimensions. I mean, the projective plane is like dimension 2 object, but it is defined as taking a dimension 3 object and modding out by some equivalence relation. And we do what we always do to get intuition. We look over the real numbers. Over the real numbers, the affine space, sorry, the affine three-dimensional space is represented like so. And we say that 2 points, let's say P1 and P2 are equivalent if they belong to the same line that passes through the origin. Okay, so in fact, what we have here, and this you can look at the notes in page 72. Every line in the 3D space that passes through the origin is a representative of an equivalence class. So we denote x colon y colon z, the equivalence class of x, y, z in the projective plane. Okay, so how do I represent it again over the real numbers? What I can do is I take the sphere, okay? Each line, let's say a blue line, a blue line that passes through the origin is one equivalence class. I can take the unit vector in the positive and in the negative direction of this blue line. So I can choose either to represent the whole blue line. So what I get is that the projective plane over the real numbers is simply, when you could take the upper half of the sphere and apart from the bottom circle of the upper half of the sphere, every point in the upper half would represent a line passes through the origin, right? This line, and in the points on the basis circle, I would need to identify antipodal points because they will belong to the same line. Okay, so you could visualize the projective space, sorry, the projective plane over the real numbers as an upper half of the sphere, in which in the basis circle you identify two opposite points. Yes.
I'm sorry, I'm not sure I understand. Why do you take only the upper half? So why do you not need to take the opposite points when it's
Because
z is not equal to 0?
Because this point is equivalent to this point. If they lie on the same line that passes through the origin, they are equivalent.
Okay.
Right? To say that two triples x, y, z are the same up to a multiplication by lambda is to say that they lie on the same line that passes through the origin.
Sounds good. Okay, I see.
Okay. Okay. So now, this is for the kind of to help you overcome the psychological barrier. But what I defined is valid for any field. We call points with a z coordinate, or maybe I can write it like this: points of the form x colon y colon 0 are points at infinity. So in other words, we identify points x colon y colon 1. Again, this 1 is just I can always, I guess, x colon y colon z. If z is non-zero, then this is going to be equal to x over z, y over z, 1. Okay? And these points we call affine points. Yeah.
So essentially what we are doing here is any line that passes through the origin, we are treating this as a point in the P2. And any line that's a scalar multiple like a lambda times x is same as x. in this sense.
I mean, you could say that the line itself, what is a line? A line is a collection of points satisfying some equation. And this collection of points is the equivalence class, okay, under the equivalence relation.
Yes.
Of course, each particular point on the line is what we call a representative of an equivalence class. Right? Is this clear?
Yeah. Clear. Yeah.
Okay.
Yes.
Yeah, Carlos?
Yeah, I have one question. Are you still excluding order 2 and order 3 fields here?
Yes. I mean, actually not. I don't need to, but
How do you have a projective space with an order 2 field although? I mean, in the
well,
sense
this
of
is
the-
interesting. This is actually interesting. Okay.
lambda times whatever is gonna be whatever. Like it's gonna be the exact same thing. There's just one element. How can you have a projective? How can you projectize one single element?
Because I do have okay, I mean, it would mean that okay, so let me just make a definition. A line in PK2 is the solution set of an equation ax plus by plus cz equals 0 for some a, b, and c in the field. Okay? So it's going to be all the x colon y colon z. This is L, satisfying ax plus by plus cz equals 0. And then there is a fascinating example. It's called the Fano plane. It is what happens when you do the projective plane for the field F2. So first of all, how many points will what is the number of points of the projective plane over F2? Can anybody say?
I would say 4, like all of the combinations that you can do.
But remember that we take F2 times F2 times F2.
Oh,
We remove the origin.
So 7.
Exactly 7.
yeah.
We remove the origin and then we divide by an equivalence relation. But as you said, Carlos, the equivalence relation is nothing here because I can only lambda I'm allowed to multiply is 1, and multiplying by 1 doesn't do anything. So it's simply the same as F2 cube minus the origin, and this is 7 points. Now, I defined what is a line in the projective space, in the projective plane. So you can fiddle around with this and look what are the possible lines. And it turns out that what you get is this. I mean, one representation of it is the following. You have 3 points here, 3 points here, and 1 point here. you draw a circle like this, and a line like this, a line like this, and a line like this. And this is a representation of the projective, the so-called Fano, sorry. The Fano plane is 7 points, and every straight line or the circle is a line passing through the points. So in fact, it is the minimal model in which every line passes through exactly 3 points. Okay, and 2 distinct lines intersect exactly at 1 point.
Wow.
Yeah?
That's cool. Yeah,
So
thank you.
for your next psychedelic adventure.
Thank you for that.
All right. Now, polynomial let's say in 3 variables. We didn't define it, but okay, I can define it is a sum, say over K, is a sum of monomials A, I, J, K, x to the I, y to the j, z to the k, where Aijk is an element, is always an element in the field K. Okay, so this should come as no surprise. Let's call it F. F, X, Y, Z is called homogeneous of degree n if all its monomials Aijk, x to the I, y to the j, z to the k satisfy I plus j plus k equals n. Okay, so homogeneous polynomial of some degree, it means that the sum of the exponents of the x, y, and z in each of the monomials is some constant number n. Now, if maybe it's better to take a capital letter for this. So if F is a homogeneous of degree n, what happens when I plug in, instead of x, y, and z, I plug in lambda x, lambda y, lambda z? I simply get, lambda to the n f of x, y, z. So x, y, and z is a 0, I guess we could say. F x, y, z is 0 if and only if f of lambda x, lambda y, lambda z is 0. And this means that the set of zeros of a homogeneous polynomial makes sense also in the projective plane. So f, so let's say the solution set of f is well defined in a PK2. Now, how do I mean, if fxy is any polynomial in two variables, then I can define f x, y, z to be the polynomial z to the n, f of x over z, y over z. This is a homogeneous polynomial of degree n. I mean, and of course, here I need to have that the degree of the original polynomial was n to begin with. So if you give me a polynomial of degree, ordinary polynomial in two variables of degree n, then I can cook a canonical homogeneous polynomial in three variables of degree n. And of course, when I plug in into this new polynomial, capital F, I plug in fxy1, I get simply f of x, y. So, for example, I take this polynomial that we care a lot about, x cubed plus ax plus b minus y squared. And I want to make the homogenization of this polynomial. This is a polynomial of degree 3 in two variables. And to make the homogenization, I need more space. What I do is I simply multiply by z to a certain power all the terms that are missing missing powers. So x cubed remains as is. Then I have ax z squared. Then I have b z cubed. And then y squared times z. Okay, and of course f of x y1 is going to be simply the original polynomial fxy. Okay, so far is it clear? All right. Yeah. Thomas?
Sorry, I just want to say it's clear.
Okay. All right. So now, what is the projective version of a line? I take a line. I mean, example. If L is let's say y equals mx plus a line in the affine space A2, namely it's the solution set of a polynomial in two variables, say y minus mx minus a, then I take the homogenization, and I get y equals mx plus a z is a line in the projective space P2. Right? This is the homogenization of the previous line, and the points of, let's call it maybe L prime. The points of L are or can be identified as the points on L prime which are affine. Remember, affine point in the projective space are simply the points of the form x, y, 1. And indeed, when I substitute x, y, 1 into the equation of L prime, then I simply get the equation of L. Okay? And now suppose we have two lines. L1 is y equals mx plus maybe b1, and L2 is y equals mx plus b2. These are parallel lines, right? Now I take the homogenization of these parallel lines. So in P2, I get L1 prime, which is a y equals mx plus b1z, and L2 y equals mx plus b2z. And points in the intersection of L1 prime and L2 prime are simply the solution set, are solutions to the following equation. I have y minus mx minus b1z minus y minus mx minus b2z equals b2 minus b1z. And if z equals 0, then indeed I have a solution. Then y equals mx. And so mx zero is a solution to this point, to this equation. Of course, this solution I can refactor it as simply 1 m 0. Okay, and that's basically the only solution. So in the projective plane, two parallel lines intersect exactly at one point, which is a point, a non-affine point, right? A point with a 0 coordinate at a 0 z coordinate is a point at infinity. Yes.
Yeah, but can you, like, is there in the notes that you have some intuition on how two parallel lines can have an intersection? How can they intersect if they are parallel?
No, I mean they are parallel lines in the affine parallel lines.
Oh, okay. Now I understand. Okay.
Okay.
Okay, fair enough.
That's it gives you another kind of angle of what is this projective space or plane.
Okay.
So in the projective plane, we have a line at infinity. Unlike in the projective line, we have a point at infinity. In the projective plane, we have a line at infinity. Every point of this line is called a point at infinity. And it turns out that if you take any two parallel lines in the affine space, in the affine plane, then they intersect. Arnaud, you have a question?
No. What was just for what Carlos was mentioning, like that. I don't know if that's correct, but like intuitively, I imagine like in the real world, you can see like the two parallel lines of the train line, for example, and if you squeeze your eyes, you can see how they meet at the horizon line, kind of. So I don't know if this is correct, but it helps to me to imagine things.
So I'm not gonna argue with anyone's intuition. I mean, this can vary, but the formal aspect of it is explained here. Okay. And what matters to us is this. I mean, the projective version of the polynomial of the elliptic curve, right? So we now look at yes.
Yes, sorry, Matan, just one more question. According to this, which indeed kind of makes sense with what I kind of was thinking, a point which has for coordinate z0 is a point that we cannot get back into affine coordinates. That
Exactly.
it's not possible to be represented in affine coordinates. So does this kind of get back to the fact that two parallel lines might have can have an intersection in the projective space, but this projection only exists in the projective space, and the proof is that we cannot get back this this line into the affine one. Okay.
Yeah.
Okay.
This I mean, of course, if there are two parallel lines, they simply do not intersect in the affine space.
Okay.
This
Thank
you can I mean, you can easily write the equations and see that there is no solution.
Yeah.
Um,
Thank you.
okay, so now in the remaining Thomas, yes.
Sorry, I have one question. So this homogenization we used to get this into the projective space, right?
Mhm.
Where did that come from? I mean,
It comes from the fact that I want to think of A2 as embedded in P in P2. P2 is like A3 minus something modulus something, right? And I want to take xy here to xy1. This, of course, this is it's a bit of a convention, but I choose a convention once and for all. And once I choose this, then I have a canonical way to turn a polynomial, say fxy, into a homogeneous polynomial. Okay, so it actually comes from this this convention.
Okay, thanks.
All right. So now I look at the polynomial we care most about, and this is y squared. Maybe x cubed plus ax plus b minus y squared equals 0. And I look at the homogenization of this polynomial in P2. So this is in the affine space A2. In P2, what I get is maybe we call it E prime. It's still x cubed plus ax z squared plus b z cubed minus y squared z equals 0. And so, of course, points, original points, k rational points in E, they correspond to the affine points on E they correspond to x, y, 1. I mean, any point x, y that lies on the original curve, its affine version in the projective plane would lie on the projectivization of the curve. But we have something new. So what are the non-affine points of E prime in, of course, in the projective plane? So to do this, I set z equal to 0. And I get x cubed is equal to 0, which means that x is equal to 0. And of course, 0, 0, 0 is not a legitimate point in the projective plane. So 0, y, 0 is a solution, is a point. It's in fact, it's the only point. I mean, of course, 0, y, 0 is simply 0, 1, 0 is the only point, and non-affine point on E prime. Okay, and this is the so-called point at infinity. And now you could go and define tangent lines at, so this E prime is called the projective curve. It's like and of course a projective curve of degree 3 is called an elliptic curve if the discriminant, so E prime is called a projective elliptic curve if the discriminant is non-zero. Okay, and you could go on and define what is a tangent line, and you will have an analogous result saying that a projective curve of this form E prime is an elliptic curve if and only if it is smooth, or it admits a tangent line at every point. And once you did this, you can define the binary operation in terms of the projective. Of all the projective solutions for E prime. And now there is this big elephant in the room that we didn't talk about, and this is the associativity of the binary operation we defined. So this is the involved. I mean, the elementary proof for many years was unfeasible for humans to track. I mean, very few mathematicians did it, and in modern times, people just plugged it into a computer and verified. The non-elementary, there was non-elementary proofs that this is an associative operation, but they involve a theory that we will not reach. I mean, this is a so-called Riemann-Roch theorem. And then I was looking around for an elementary and feasible for human proof of associativity, and I found a paper from 2021 by some Japanese guy, and this appears in the appendix. The proof is still, it's like 10 pages or maybe 8 or something like that, but it is all done in elementary terms and in projective coordinates. So now that you know projective coordinates, you can, if you like, you can look at the appendix and see that you actually get an associative operation. And yeah,
Please share the paper.
it's in the appendix in the notes. I mean, the
Okay, good.
I can tell you. There is only one appendix at the moment. Yeah, just look over there. I mean, I don't remember the name of the paper and the author. And okay, so basically, this is a point where we skip. We might, if you really want, we might later on go over some parts of the proof, maybe some of the cases, just to give you a sense of how to prove it. But to go to the full proof, I think is not very useful. And so what we get is that for an elliptic curve over a field K, the set of K rational points is an abelian group. Yes.
Yeah, I'm sorry, it's just because we have the end. I just wanted to make a question related to Thomas' last question about the homogenization. I still don't see where do we use the fact that all the monomers, I mean, the sum of the pores of the monomers are all equal to n. Like, to me, like, why do you use this fact to transform to projective space is not something that was clear to me.
Well, because this actually, I think the answer is very easy. I mean, I'm interested in polynomials only because I want to look at the solution set of these polynomials.
Mm-hmm.
And a solution set of a non-homogeneous polynomial does not make sense in the projective space, because I want to say that if x, y, z is a solution of a polynomial f, then actually if and only if lambda x, lambda y, lambda z is also a solution of the polynomial, because I know that in the projective plane x colon, or maybe, yeah, yes, x, y, z is equivalent to lambda x, y, and z. So to say that, I mean, to be able to make sense of talking about zeros of polynomials, I must have a homogeneous polynomial. Is this clear?
Not really. I don't see why do we to find the roots of the polynomial.
Let me give you an example. I mean, let me give you an example. Yeah. I mean, I take this polynomial f f x y z is x plus 3. Okay, that's a legitimate, or maybe x plus 1. Okay, it's a legitimate polynomial over any field, but it's not a homogeneous polynomial. So what are the zeros of this polynomial? I mean, it's all the points, so the solution set of f in the affine space is simply the collection of all x, y, z, such that I mean, x is equal to -1, so it's simply -1, comma x, comma y. But now I look in P2, and I find that -1 x, y, it must be a solution for this polynomial, right?
Mm-hmm.
But now I rescale it. I multiply, let's say I multiply everything by -1. This point is simply equal to 1 comma minus x comma minus y.
Yep.
And this point is not in the solution set. I mean, if I substitute it in the polynomial, it's not. So I have like a paradox. I have 2 points that are equal, but if I substitute naively their coordinates into the polynomial, one time I get that it's 0, and in another time I get it's non-zero. Okay, so the point of homogeneous polynomials is it's the only sensible way to talk about solution set of polynomials in the projective plane, because I have to have, so I mean I have to have a polynomial with the property that if x, y, and z is a 0, then I must then also lambda xy, lambda skill, lambda y, lambda z is 0.
But in this case, how does this solve the problem? In this specific example of x plus 1, how does this solve the problem?
X plus 1 is not a homogeneous polynomial because it has a monomial of degree 1 and a monomial of degree 0.
Yeah, sure. If we make it homogeneous,
okay,
how does
if you
it
make
solve
it
the problem?
homogeneous, then I multiply it by z, and now it's okay, right? Now the solutions, I mean, solution set of polynomial x plus z. This is well defined. I mean, let's call it G. If this is a homogeneous polynomial, so if x, y, and z is a 0 of this, namely if x is equal to minus z, then also g of lambda x, lambda y, lambda
Oh,
z.
I see. Okay.
Okay, so that's the
Oh,
point.
I
It's
see.
like because of this equivalence relation, you cannot talk about zeros of polynomials that are not homogeneous.
Makes sense. Okay,
Right.
thanks.
Okay, let's stop here unless you have other questions or.
I have one more. I understood homogeneous polynomials as polynomials whose each term has the same degree. Each non-zero term.
Each monomial, yes, each monomial.
Yeah. Okay. So it's this criteria that we're applying. Fair enough. Okay.
Yeah.
Okay.
All right. Have a great weekend, and see you next time.
Thank you very much.
Likewise.
Bye-bye.
Thank you. Bye bye.